In this video, we're going to continue our study of integration by parts, but we're going to extend what we've done to looking at definite integrals. A reminder that definite integrals are integrals over a specific interval. So if we imagine what this graph might look like from 0 to pi, then whatever the graph looks like, maybe a sine, something, who knows. But if we go out to pi, we are asking for the area under the graph, if it's positive, or the grand total of areas above minus areas below if it ends up being negative. The idea, though, is this is a number at the end of the day. There's a value for this integral because we are spanning a very specific interval on the x-axis. Fortunately, there's not a lot of complications with using a definite integral with integration by parts. The only thing we have to remember is one of the terms that we get doesn't have an integral. We just have to remember that it should be evaluated at pi and at 0 as well. Let's work through this example. We've seen other examples with this kind of flavor of x times a trig function. So we'll go straight to what we've seen is fairly effective. We choose u to be x because we can differentiate it and the x will go away. And the sine of 4x we can certainly integrate and it doesn't get any more complicated. So when we differentiate x, we get 1, and a dx I would bring up. On this side, the integral of 1 dv is v, and to get sine of 4x, I would have to differentiate cos of 4x. I would need it to be negative, because the derivative of cos would be negative, and we don't want that. And we would also need to divide by 4 to generate the canceling of the 4 and the 4 to get back just a sine of 4x. So we do expect you to be able to do these guess and check integrals as needed as a component of the integration by parts process. Let's name this integral here I. Our integral is then replaceable by u times v, so x times negative cos of 4x all over 4 minus the integral of v du, the second arrow, so negative cos of 4x all over 4 times dx. And we have the integral from 0 to pi. Because the integral is still with respect to x, we're still integrating from 0 to pi. The thing that we have to be careful about is this function here also needs to be evaluated from 0 to pi. What I prefer is to write that explicitly in the notation here, but know that we still have some integration left to do, so I don't bother doing the subbing in until the very last step, and we do it for all the points all at the same time. Again, for integration by parts, it's usually worthwhile tidying things up a little bit, just so you can see what you're dealing with. And specifically here we have plus 1/4 the integral of cos of 4x. There we can focus on the actual integrand that's meaningful and bring any negative sign corrections and constants out front. Fortunately, this integral here is simple enough to do by inspection. So we will have everything from before, cos of 4x, plus 1/4. I would have to differentiate sine to get cos. It would also have to be sine over 4 to correct for the 4 inside. And we can do the plus c if you want, but the key thing is it'll be the integral from 0 to pi of this entire expression. Which leaves us with one last step of subbing in the pi and the 0 into this antiderivative formula we've just generated. If we give ourselves a little space, we can complete that right here. If we have pi, we're going to have negative pi over 4 cos of 4 pi. Think about that for a second. Cos of 0 is 1, cos of 2 pi is 1, cos of 4 pi is, oh, that's just 1. Plus 1/16 sine of 4 pi but sine of 0 is 0, sine of 4 pi, 2 pi, all those multiples are also 0, so that's times 0. And if you want, you can do the plus c, but we also know it's going to cancel on the other side. So here we're evaluating at pi, and then we're going to sub in the 0, which turns out to be even easier because we have 0 here, and sine of 0 is 0. That all goes away, and so our final answer is simply negative pi over 4. Let's reinforce that approach with another example. Let's consider the integral from 1 to 2 of ln of x dx. Now, there's some muscle memory that kicks in here and people think, oh, that's 1 over x. Well, no. We know the derivative of ln of x is 1 over x. What we don't have is the integral of ln of x. What's the antiderivative of ln? Fortunately, we can tackle this by integration by parts. There's only two things in here, and the dx has to go with dv. So the question is, where could we put ln of x? If I put ln of x here, I'm just going to have to integrate it, and if I knew how to integrate ln of x, I wouldn't use the integration by parts. So if we put the ln of x in the u part, though, we get to differentiate ln of x. Oh, we know how to differentiate ln of x. So this is a fantastic application of integration by parts, even if there's only one element in the integral, because it lets us trade the integral for a derivative, and derivatives are something we're much better at in general. Let's see how that plays out. So our derivative of ln of x is 1 over x. So we get du is 1 over x dx. When we integrate this other part, there's no problem. We're going to get v, and the integral of 1 dx is just x. Put our little mnemonic arrows here. Our integral, call it I, is going to be u times v, so ln of x times x, minus the integral of v du, x times 1 over x dx. The integral is from 1 to 2. We keep those limits of integration, and we also apply them to the first leading term that no longer has an integration involved. Again, tidying up makes relationships look a little more straightforward. X ln of x between 1 and 2 minus, oh, x over x is just 1. Have we traded this for a simpler integral? No question here. It doesn't get much simpler than just the integral of 1. So now we can integrate that one last step. And when we do that, we don't touch the first part, it's done. But we just integrate 1 with respect to x. That gives us x between 1 and 2 as well. And so we can just do the subbing in part, the 2 and the 1. We're going to have 2 ln 2 minus 1 ln of 1 minus 2 minus 1. Quick check, ln of 1 in fact is 0, so that term is going to disappear. And so we get 2 ln of 2 minus 1 at the end of the day. And what that tells us, we do have a visual for this. The graph of ln of x on the graph x here, from the point 1 over to the point 2, the area underneath the graph of ln of x on the interval from 1 to 2 is this region here, and that region there has the exact area of 2 ln 2 minus 1.